In this video, I want to take a further look and just a little bit more explanation, another example of chemical equilibrium, how to write the equilibrium constant expression here, and then once you have a numerical value for the equilibrium constant, what does that mean to interpret it? So I know we've done an introduction to chemical equilibrium, but I'd like to do some further explanation and further review. So here what we've got is we've got a reaction. It looks like it's a decomposition reaction from this dinitrogen pentoxide gas down to an NO2, a nitrogen dioxide gas, and some just pure oxygen gas. Now, we've balanced the equation, a 2, a 4, and an implied 1 here. And we're going to write the equilibrium expression. Now remember, that is just a ratio that is of the concentrations of the species reacting, and the stoichiometry is shown in the expression. Now, in our earlier video on Introduction to Chemical Equilibrium, I told you there were some species that had to be excluded from the expression, that had to be excluded. Take a moment. Do you remember what those were? If not, that's okay. That's why we review further and continue to review. We exclude any species that are pure solids or pure liquids. In our example here, we have 3 gas species, so we include all of those. Now, why do we exclude the pure solids and the pure liquids? Because their concentration doesn't change over time. They're pure solid, pure liquid. They're not a mixture. Think of it as there's no solvent, no solute relationship, because it's not a mixture, it's not a solution, it's not a measured molarity concentration. It's a pure solid or a pure liquid. Now, we write this expression. Remember that we use square brackets. Square brackets represent molarity values. Okay, so anytime in chemistry when you see square brackets, those are representative of molarity concentrations. And remember that molarity is equal to the moles of solute per liter of solution. Okay, liter of solution. Okay. So we are looking at a molarity value. Moles per liter. Moles per liter is what we're looking at. We also remember that we put the products on top. They're our numerator. The denominator is your reactants. It's always products over reactants. Products over reactants. We write these equilibrium constants relating to the forward reaction. We realize that it is a reversible two-way reaction, but when we write our K expressions, we write those in terms of the forward reaction. If we wanted to reverse, see what the K value is for the reverse reaction, we just do the reciprocal of it. Just flip it over. Okay? So always write your equilibrium expressions in terms of the forward reaction. So it'll be the products over the reactants. Now when we get those values, okay, here's a picture for us to relate to. Okay? And I'll move it down when we look at this second reaction in more detail. This first reaction, we have some hydrogen gas with some bromine gas, and we're forming some HBr, some hydrogen bromide. We can see there we got these little molecule models here for us. Now equilibrium is established in the reaction system, and let us not forget, equilibrium establishment means the forward and the reverse reactions, the opposing reactions, are proceeding at equal rates. Okay, that's what chemical equilibrium is. The opposing reactions, the forward-reverse reactions, are proceeding at equal rates to one another. So we have an equilibrium established here. Now, we write our expression. Remember that we use the stoichiometry. Those coefficients become exponents in our expression here. Now, we can see from this visual model that at equilibrium, there are far more HBr species. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like 11 there. 11 of those species compared to 1 of the hydrogen and 1 of the bromine species there. Okay, so that's going to give us a rather large number. When our K expression, when this value right here is, when value is above 1, okay, is above 1, okay, or is much, much greater than 1, far greater than 1, it's a very large number, say it's like 5,000, 10,000, 20,000, whatever it may be, it's far above 1, that is telling us that the product species are the dominant, the most prevalent, the overwhelming majority of species when equilibrium is established, okay, that their concentration is extremely high. Okay, in this second reaction I have here, we've got some nitrogen gas and oxygen gas reacting and making some nitrogen monoxide here, some NO gas. Okay, equilibrium is established. The forward and reverse reactions are proceeding equally. We write our expression. Again, notice the stoichiometry comes into play. This shows us a very small number, okay? Let's count the number of nitrogen molecules here left at equilibrium. There's 1, 2, 3, 4, 5, 6, 7 of those at equilibrium. Our oxygen here, there's 1, 2, 3, 4, 5, looks like 5 of those at equilibrium. And the NO, it looks like here's 1, 2 of those is all we have. Okay, if this expression gives us a value, a numerical value that is a value below or much, much below 1 in value, that is telling us at equilibrium, okay, at equilibrium, what we will notice is that the reactant species will be the far common, the far majority of all substances present. Okay, so when we numerically determine these equilibrium constant values, we look at those numbers and we can make some insight on which chemical species are most dominant or most prevalent at equilibrium. Is it, in this case, the products that are most common, most concentrated, or is it the reactants that are most common or most concentrated?